Hello, can you hear me? Hello,
Hello.
yeah, we'll finish whatever else is left in the chapter. So, basically, in gravitation, we have already covered the basics and field and potential stuff. So, now what is left is planets and satellites and escape velocity and Kepler's laws. These
Right.
three topics are pending. So, we start off with understanding how planets and satellites are moving. So, if you have, let's say, Sun and Earth is here and is trying to go around in a circle around the sun, then obviously it is going at a speed v, and the force of attraction is gravitation force.
Right.
If the radius of the orbit was r, then we can say that for the Earth, the Newton's law equation is Fg is equal to mv square by r. If it
Right.
is moving in a circular orbit of radius r, the equation should be this, right?
Right.
And Fg is going to be G capital M mass of sun, mass of earth by r square is equal to mv square by r. Here you are taking advantage of the fact that since the sun is considered to be a sphere, the force due to the sphere is as if the sun was a point particle at its center.
Right.
Because we know that field due to a sphere outside the sphere is as if the whole sphere is concentrated at the center, right?
Right.
So this r is the distance between the center to the center,
Right.
right?
Yeah.
So from here, we can easily figure out that the speed of the Earth in orbit, in a circular orbit, is root over G capital M by small r,
Right. Yeah.
right?
Yeah.
This equation is valid for all circular orbits. All circular orbits, this is going to happen. Because obviously the same type of equation will come. You have to realize that even if it's a satellite going around the Earth, what matters for speed of the satellite is the mass of the Earth and the radius of the orbit, not the mass of the satellite.
Right.
If you have another different mass satellite, that will also be going at the same speed if the orbital radius is same and if the mass at the center is same,
Right.
right?
Yeah.
So if you change the radius and if the satellite is at some other radius, then obviously the speed will change.
Right.
And this equation also implies that as r increases, the velocity of the satellite decreases.
Right. Yeah.
So if you want to rotate near the surface of the sun, you have to go really fast
Right.
because the force of gravitation is much stronger. So you have to go really fast in order to fall towards the sun, but at the same time, you're going so fast that the sun's surface is also curving.
Right. Yeah.
You're maintaining an equal altitude, right?
Right.
You're technically falling, but you're going so fast that by the time you fall some distance, the surface of the sun itself curves.
Right. Yeah.
So you are in orbit at the same height with respect to the sun.
Right.
So if you go far away, you can go at a more slower pace. But if you are closer, you have to go really fast.
Right.
So this gives us the orbital speed of any satellite around any mass. Now, using that, we can figure out what is the kinetic energy and potential energy. So V is coming out to be root gm by small r, where small r is the radius of this orbit. So kinetic energy is coming out to be half small m, because mass of this body is small m, v square, which is half m G capital M by R.
Right.
So you're getting this as the kinetic energy inside a particular orbit.
Right. Yeah.
If you think of potential energy of these two bodies, you can consider them as point masses for this calculation, and you can take potential energy as minus G M by R. Right?
Right.
You are considering both of them as spheres, and you are saying potential energy is this. And now we can say that the total energy of a body which is in orbit, in a circular orbit around a planet or something, will be Ke plus Pe, and that is Gmm by 2r minus Gmm by r. So you can see that the total energy comes out to be negative.
Right.
The total energy is minus Gmm by 2r, and the modulus of total energy is same as the magnitude of kinetic energy.
Right.
Because potential energy is minus 2 times Ke.
Right.
So these relationships are valid, and total energy is basically the same as kinetic energy but with negative sign, right?
Right.
Now this is a very important idea because it tells us that anytime a body is going around a planet and it is in orbit around a planet, it is basically what we call a bound system. A bound system in the sense that the satellite is bound to the planet. It's not like free to go wherever it wants, right?
Right. Yeah.
And if you have a bound system where there are multiple masses which are going around each other and they cannot escape each other's gravity, in such a situation, the total energy of the system or of the body which is bound is always negative.
Right. Yeah.
Total energy of my body M came out to be negative, right?
Right.
And technically, you are taking total energy of the system because you are assuming right now mass M is fixed, so it has no kinetic energy, right?
Right. Yeah.
Total energy of the system, you are saying, is equal to kinetic energy of small mass plus potential energy of the combination, right?
Right. Yeah.
So you're getting total energy of a bound system is negative, right?
Right.
Now, using that idea, you can realize how you can escape from the Earth's surface, or whether it is possible to escape from the Earth's surface using a rocket. So let's say this is the Earth's surface, and the rocket was first, it was stationary on the Earth's surface. So this is capital RE, the distance from the Earth's center. So potential energy right now is minus Gmm by RE, right?
Right.
Here M is mass of the Earth and small m is mass of the rocket, right?
Right. Yeah.
This is the potential energy, and you burned some fuel to get some kinetic energy right now, let's say, right?
Right.
You acquired kinetic energy after you started the engines and burned some fuel, right?
Right. Yeah.
Now, when it was at rest, when it was at rest on the Earth's surface, or actually, like we don't need to take that case. What we can say is you should realize that as you go up and up, what will happen is kinetic energy will reduce and potential energy will technically increase, right?
Right.
Why? Because this becomes bigger, right?
Yeah. And negative sign. Yeah.
And it is negative sign, so it's a smaller negative, right?
Right.
As you go away, it will become smaller negative.
Right.
And obviously, kinetic energy is reduced because force of gravity is trying to pull it back, so it is a decelerating,
Right. Yeah.
right?
Yeah.
So your total energy value is technically going to change now, right?
I can.
Total energy will change from whatever was there in the beginning. I mean, it doesn't really change because conservation of energy of the whole system.
Yeah.
So what you can say is at this moment, if the velocity is v dash, it is half m v dash square, and whatever is the potential energy at this height should be equal to half m v square minus g m by re, right?
Right. Yeah.
This is the statement of conservation of energy of the entire system,
Right.
because Earth is supposed to be not moving, right?
Right.
You have assumed Earth is not moving, so you are balancing the kinetic energies and the total potential energy of the system,
Right. Yeah.
right?
Yeah.
Now the point is that if your initial starting value here was less than 0, if your initial starting value here was less than 0, you can never escape. You can never escape Earth's gravity. Why? Because if it was less than 0, then no matter what you do, this is also less than 0, right?
Right.
But think about what happens if initial starting value was equal to 0 or more than 0, right?
Right.
If you got enough kinetic energy that this exceeded the negative potential energy at the surface, then what happens is you could potentially reach infinite separation, because at infinite separation potential energy is 0, and maybe you reached infinite separation with 0 kinetic energy, right?
Right. Yeah. Yeah.
You kept slowing down, and eventually you almost stopped, but you have reached infinite separation, right?
Right. Yeah.
At that moment, your kinetic energy is 0, but potential energy is also 0, and your total energy is 0, right?
Right.
But that can only happen if initial total energy was also 0, right?
Right.
Suppose initial total energy was greater than 0. In that case, you can reach infinite separation with positive kinetic energy, right?
Right.
So that means you have reached infinite separation and you have a velocity, so you have really escaped now.
Right. Yeah.
But if your total energy initial was less than 0, what will happen is you will not be able to reach infinite separation, because if you reach infinite separation, then potential energy became 0, then kinetic energy has to be negative, which is impossible.
Right. Yeah.
Because of the equation, this must be equal to this. If this is negative, then potential energy at infinite is 0, right?
Right.
That would mean kinetic energy is negative there, which
Right.
is
Yeah.
not possible.
Yeah.
So that means you can't go to infinite, you have to stop at some finite point only.
Right.
You will reach some finite distance where kinetic energy becomes 0, but potential energy is equal to that negative value.
Right.
And after that, you are still in the field of gravity. So you will start coming back after that.
Right. Yeah.
Do you understand what I'm saying?
Yeah.
So the basic condition for escaping is that total energy is greater than equal to 0 at the surface of
Right.
the earth, or wherever you start the escaping point, wherever you want to escape from, right?
Right.
If you want to escape from the surface of the earth, you need to make your total energy at the surface of the earth greater than equal to 0,
Right.
right?
Yeah. Yeah.
In case you are already in orbit, you might have some total energy right now here, but you need to burn extra fuel so that your total energy now exceeds 0 here, right?
Right.
Unless your total energy exceeds 0, you cannot change your state from a bound system to a free situation.
Right. Yeah.
So this gives us a condition for finding escape velocity from the earth. You can say total energy at surface of earth must be greater than equal to 0. So at the surface of the earth, let's say you got kinetic energy half mv square. Potential energy was minus g mm by r of the earth, greater than equal to 0, right?
Right.
This is for escaping, correct?
Right.
So you get half mv square is greater than equal to g mm by re, and you get basically v is greater than equal to root over 2g capital M by re, right?
Right.
If you calculate the value of this using the data for Earth's radius, which is around 6,400 kilometers, and Earth's mass, which is I think roughly like 6 into 10 power 24 kg, and G, which is 6.67 into 10 power minus 11, right?
Right.
You should get something like V is greater than equal to 11.2 kilometers per second.
Right. Yeah.
So you need to acquire a speed of 11 kilometers per second near the Earth's surface, and then only you will be able to truly escape the Earth's orbit.
Right.
The actual value of this is not important. What is important is this formula for escape velocity,
Right.
right? So this formula will also be valid for any mass which is holding another body to it, right?
Right. Yeah.
As long as you're calculating it from the surface. It is also possible that, let's say, sun was here, earth was here, earth is in orbit right now. Total energy of the earth is minus gmm by 2r, right?
Right.
M is this and m is mass of the sun, right?
Right.
So if earth wants to escape the orbit of the sun, it needs to get from some source some kinetic energy extra. It already has a kinetic energy, right?
Yeah.
It already has both of them, but it needs to somehow get an extra kinetic energy which will be equal to gmm by 2r, right? At least.
Right. Yeah.
So it needs an extra that much kinetic energy, right?
Right.
Then its total energy will be zero, and then it will be able to escape along this straight line path,
Right. Yeah.
right?
Yeah.
So that becomes your formula for escape velocity, root 2 gm by r. And obviously, what we see from here is this: if the ratio of m by r increases, the escape velocity increases, right?
Right.
So it is roughly like a density of the mass, right? Like the mass of the star or the body that is holding you divided by the radius of the orbit, right?
Yeah. Yeah.
Or radius of the star if you want to escape from the surface of the star.
Yeah.
So technically, if a lot of mass is concentrated in a small radius, then it will be difficult to escape from that body, right?
Yeah.
So if you reduce the r or increase the mass a lot, then the escape velocity will increase,
Right.
right?
Yeah.
So that is the concept of a black hole. Black holes are at the center of every galaxy, almost every galaxy, and what happens is a lot of mass, like a mass much greater than the sun's mass, is concentrated in a really tiny area. Like it's concentrated in a small dot, almost like a pin drop. If you have mass of the sun or more than the mass of the sun actually is concentrated in a very small area, the escape velocity of the black hole becomes super large, and it is called black hole if the escape velocity becomes greater than the speed of light.
Right.
This value can be as large as possible, depends on how concentrated your mass is, right?
Right.
If your escape velocity is greater than the speed of light, then not even light can escape.
Right. Yeah.
Nothing can escape. Nothing is faster than light, and if light cannot escape, then it becomes like a dark spot, which is known as a black hole.
Right.
And it is the black holes that are driving all the stars and all to keep going around the galaxy center. Like Milky Way galaxy has billions of stars, and it's all going around a super massive black hole. Everything goes around it. The black hole has a lot of gravitational attraction.
Right.
All the stars are going around it. So anyway, that is not super important right now. So basically, we have seen energies of planets in orbits and so on. Now, we also saw planetary speed was, or satellite speed was this. And from here, we can find the time it takes for a satellite to go around a full orbit, right?
Right.
This is the Earth and this is the satellite. We know the speed is this, radius of the orbit is r. So time taken to complete an orbit will be distance by speed. 2 pi r is the distance, speed is this. You have to realize that as long as you are in the same orbit, your speed cannot change.
Right. Yeah.
So you are moving at constant speed in the circular orbit, and so your time period will be 2 pi r by root gm by r, so it will be r power 3 by 2. So you're getting time period is 2 pi r power 3 by 2 by root gm, right?
Right.
And from here we can square it and write it like this, 4 pi squared by gm and r cube. And then we get this result that time period square is proportional to radius cube, right?
Right. Yeah. Yeah.
So for different satellites which may be in different orbits, you can compare the time periods and the radius in this way because of this relation, right?
Right.
So this is your Kepler's second law or third law, whichever one. Kepler's law of orbits, right?
Right.
So one of the laws is this: the time period square is proportional to radius cube for any planet or satellite going around a central mass, right?
Right.
So this explanation is super easy because we know our law of gravitation and we were able to fully get the speed of the satellite using our basic Fg is equal to mv square by r and all.
Right. Yeah.
So it's very simple to realize that from Newton's law of gravitation, we are able to derive this. But Kepler got this law when there was no Newton's laws of motion or no gravitation. He was 50 to 100 years above before Newton. So he got this law by just looking at data of planets and satellites and how they move in the sky. So
Oh, okay.
that time it was totally unbelievable, and it is like a remarkable thing that he was able to look at the stars positions in the sky or planets positions in the sky over years and years, and from the data he was able to predict that this is the relationship.
Right.
Post Newton it is easy to see why, right?
Yeah. Yeah.
So that is one law of Kepler. The second law, or actually the first law, is that all planets move around in elliptical orbits with the sun at one focus of the ellipse. Focus of the ellipse. So what is the meaning of this? An ellipse is a curve like this, and there are two foci for an ellipse, right?
Right.
You have studied coordinate geometry, right?
Yeah.
So the planets are moving around in elliptical orbits. This is the sun, one focus, and the planets keep going around like this. And if you draw your axis and all, you can say that this is your 0, 0, this will be minus AE comma 0, this will
Right.
be AE comma 0, this is your 2B, right?
Right.
This is your 2A. You should know all this, right?
Right.
You know the basic ellipse structure and all, right?
Yeah.
You should know that there is a relation E square is equal to 1 minus B square by A square. E is the eccentricity.
Yeah.
So this is the eccentricity of the ellipse. And you can see from here that this point is minus A comma 0 and this point is A comma 0. So the planets are not at same radius from the sun all the time, right?
Right.
Sometimes they are farther, sometimes they are closer. The closest distance is basically A minus AE, right?
Right.
And the largest distance is A plus AE,
Yeah.
right?
Yeah.
And at other times they are at intermediate distances between this and this,
Right.
right?
Yeah. Yeah.
For most of the planets, the eccentricity of the ellipse is very close to zero. For example, for Earth and all, the orbit is such that it's not really, it's very close to a circle. If the eccentricity is zero, it's a circle, right?
Yeah.
So most of the times we can use our circular orbit approximation.
Okay.
For example, for Sun and Earth, we can roughly use our circular orbit calculations. All the formulas that we have seen, root gm by r and all, are valid for circular orbits, right?
Right. Yeah.
We have not derived anything for elliptical orbits. So we can use circular orbits most of the time, but not for weird planets and all like Neptune and all, which are slightly more elliptical in nature.
Right.
Like Sun and Earth or Mars and all are mostly roughly circular. The eccentricity is close to zero,
Right.
right?
Yeah.
If the eccentricity is close to zero, you can see that this distance and this distance is roughly same.
Right. Yeah.
So the first law of a Kepler is that they move in elliptical orbit. Sun is at one focus and the planets are moving around like this. This is the shortest distance, which is known as perihelion, I think. And this is known as aphelion, which is the largest distance. Or maybe reversed, you have to check. So aphelion would be this distance, A plus AE, and perihelion will be A minus AE.
Okay.
Right?
Right.
1 second, hold on. Okay, so fine. So this is first law. The other law we already saw is T square is equal to 4 pi square by GM R cube, right?
Right.
That law again we derived using circular orbits. The derivation using elliptical orbits is quite complicated, so we'll not be doing that. But roughly for circular orbits, it is obvious to see how this comes, right?
Yeah.
And the final law is super important. It says that the radius vector from the planets to the sun sweeps out equal areas in equal time, right?
Right.
Do you understand what this means?
Yeah. Yeah.
What is the meaning?
So, like, if we assume that the body's at the far leftmost point, uh, then at a time t, uh, we can say it goes from how much ever it covers, that much area in that time t. Then, if we take a different location in the
Mhm.
same time t, even if the shape might be different, the area will still be the same.
Okay. So basically, the idea is that if you start from some point A and in time t it has gone to B, right?
Right.
The radius vector is this vector, and this is the new radius vector after time t, right?
Right.
This area is the area covered by the planet, and with the sun as the center, this is the area that it sweeps, right?
Right.
And if you start at any other time also, let's say at C you start measuring, and then it has gone like this till D, right?
Right.
If you cover the same time, then this area will be equal to this area,
Yeah.
right? The point is that as you come closer, your speed is higher, right?
Right.
And as you are farther, your speed is lower, right?
Right. Yeah.
Even if the distance here is big, the speed is lower, so it covers only a small base, right?
Right.
While here, even if the radius is small, the speed is higher, so it goes a bigger area here, right?
Right.
Bigger distance so that the area becomes same.
Right. Yeah.
Now, the proof of this is important to realize why it is happening like that. So, if you take the sun like this, and let's say this is r vector, and after some time, small time, you have gone to this location r plus dr, right?
Right.
So technically you have swept an angle of d theta, okay?
Right.
You have gone from this r vector to a slightly shifted vector in time dt. In a small time dt, you have gone, right?
Yeah.
So I want to figure out what is this area, right?
Right. Yeah.
So what I can say is, because the time taken is really small, I can say that this is roughly a straight line, right? Roughly.
Right.
So then it is like a triangle, right?
Yeah.
And the distance here at the end of the arc would be r times d theta, right?
Yeah.
That is the base of the triangle.
Right. Yeah.
So if you look at this triangle, the radiuses are roughly same, only r and r, but not much has changed, right?
Yeah.
And you can
Yeah.
say area of the triangle DA will be equal to half r into r in, actually you can write it like this also. And you can say sine of d theta.
Right. Yeah.
Do you understand? This is coming from half BC sine
Yeah.
area of any triangle, right?
Yeah.
So if you think about this, this is a small angle, so we can write it as d theta only.
Yeah.
Sine d theta is similar to d theta, and we can get this as half r square plus r dr into d theta. So dA is coming out as half r square d theta plus half r dr d theta, right?
Right.
This has two small quantities, so we can ignore it.
Right.
Two
Yeah.
small quantities are being multiplied. Here only one small quantity, right?
Right.
So we are getting dA is roughly same as half r square d theta.
Right.
This is the area that was swept in time dt. So what is dA by dt? That will be equal to half r square d theta by dt.
Right.
And d theta by dt is the angular speed of the planet around the sun, right?
Right. Yeah.
Half r square omega, right?
Right.
Great. So now half r square omega is coming as my rate of area being swept, right?
Right.
Now if you think of the sun and the planet as a system, sun is here, planet is here, and let's say this was your r and this is your theta angle, and d theta is a small displacement that happened, and the rate of this change is omega, which is d theta by dt, right?
Right.
Now the force on the planet was towards the sun, right? Like this.
Yeah.
Force of gravitation was towards the sun. So obviously this force of gravitation does not create a torque about the sun
Yeah.
because it is passing through the sun,
Yeah.
about sun. So there is no net torque on the system about the sun.
Right.
If there is no net torque about the sun, then L about sun will be conserved.
Yeah. Yeah.
Conservation of angular momentum will happen because there is no net torque on P about the sun, right?
Right.
An angular momentum of P about the sun would be I omega because it's a pure rotation, right?
Yeah.
I would be mr square omega, right?
Right.
Pure rotation, L is mr square omega, right?
Right.
Think of it as a roughly circular motion for now. That's what we are doing, right?
Right.
And if L is mr square omega, L by 2m is basically half r square omega, right?
Yeah.
So what we are getting really is that dA by dt is equal to L by 2m,
Right. Yeah.
where L is the angular momentum of the planet about the sun,
Right.
and m is the mass of the planet.
Right.
So because dA by dt is equal to L by 2m and L is conserved about the sun, right?
Right.
Therefore, this part is constant,
Right. Yeah.
which is the proof or the logic behind why the area swept is constant with constant time.
Right.
Rate
Yeah.
of area being swept is constant because L is constant and M is
Right.
obviously constant.
Yeah.
So this tells us that since L is conserved, if sun was here and planet was at two different locations which are far away and all, if this speed is v1 and this radius is r1, this speed is r2 and v2, obviously we can say L will be same. So we can say m1 v1 r1 should be m1 v2 r2, right?
Right.
We have v1 r1 is equal to v2 r2.
Right. Yeah.
So which means that if you want to compare these two locations, you can easily say V1 by V2 is R2 by R1, and R2 by R1, if you think about it, is A1 minus E by A1 plus E.
Right. Yeah. Yeah.
1 by V2 is coming out to be 1 minus E by 1 plus E.
Yeah.
So at any point, and it's not like with just these 2 points, L is always same about the sun, no
Yeah.
matter where you are, right?
Right.
But for other points, you'll have to actually do the cross product properly.
Yeah. Yeah.
So since we don't know the angles and all, I'm not taking those cases. But
Right.
technically, L is conserved. That's why dA by dt is L by 2m is the constant,
Right.
right?
Yeah.
That is the explanation for Kepler's law. Now, I think everything that is required is done. Uh, have you tried any questions in the chapter?
Yeah.
Do you have any doubts?
Yeah.
Tell me
Uh,
which ones.
in the solved examples, the 13th one.
Okay. Two satellites S1 and S2 rotate around a apparently coplanar circular orbits in the same sense. Their periods are 1 hour and 8 hours. Radius of orbit is this. It is super easy. No? When S2 is closest to S1, find the speed of S2 relative to S1. From the figure, you can see S2 is the bigger orbit and S1 is the smaller orbit, right?
Yeah.
The time periods are given in the ratio of 1 is to 8. So obviously we know T1 by T2 is equal to R1 3 by 2 by R2 3 by 2, right?
Right.
So we can get the ratio of R1 by R2 from here.
Yeah.
R1 by R2 is T1 by T2 to the power 2 by 3.
Right.
So that is 1 by 8 to the power 2 by 3, which is 1 by 4.
Right. Yeah.
By using Kepler's laws, we are getting 1 by 4 as the ratio.
Right.
So once we know the ratio, orbit of S1's radius was given. So we know now orbit of S2's radius, right?
Yeah.
If you know the radius, you can find the speed in the orbit by doing root gm by r1 and v2 is root gm by r2.
Right. Yeah.
So if you know the speeds now, obviously you can find relative speed, no?
Yeah. Yeah. I got it.
Depends on how they are oriented at the moment you are calculating relative speed. That's why he said at the same moment when they are aligned like this.
Right.
If they are aligned like this, then you can easily take relative speed by subtracting. If
Right.
you were measuring relative speed when one of them was here and one of them is here, then you have to do proper vectors and all,
Right.
right?
Yeah.
The next part is angular speed of S2 as observed by astronaut in S1. Angular speed of angular speed is basically 2 pi by t, right?
Yeah.
So angular speed will be different because T1 and T2 are different, right?
Right.
So again, you calculate the angular speed of both of them from a ground frame and then take the difference and all, right?
Yeah. I got it. Yeah.
Okay, you can read the explanation, it should make sense. What is the
So,
next?
yeah. So, in one question, I think the ninth one,
In
I
the
had solved it.
exercise or in the example?
Exercise.
Gravitational field due to a rod of length L mass m at a point on the perpendicular bisector.
I had reached an integration, but I didn't know how to do it.
You have to find field at a point on perpendicular bisector at a distance d. So this is distance d, length L, mass m for the rod. Obviously, if I take a small mass here dm, field due to that will be like this.
Right,
At point P, field is in this direction, but this is my dE, let's say. But similarly, there is an opposite point here at the same distance, let's say x.
right, yeah,
Field here would also be like this, right?
yeah,
So you should realize that the components in these two directions will get cancelled, right?
yeah,
So if my angle is theta here and this angle is 90 minus theta, d cos 90 minus theta gets added.
right,
So it is d sine theta that gets added, d cos theta gets cancelled, right?
right,
All we have to find is d sine theta, right?
right,
Due to this mass and then integrate it to cover the whole rod, right?
right, yeah,
So dE expression due to this mass dm would be g dm by whatever is this distance square, which is x square plus d square, right?
yeah,
And d sine theta would be d by this root of this, right?
right,
So g dm d by x square plus d square to the power 3 by 2,
right,
right?
yeah,
And dm can be written as m by l dx.
yeah,
So you can write this as g dm by l dx by x square plus d square to the power 3 by 2,
right,
right?
yeah,
Now everything is in terms of this x variable. You have to integrate. X goes from minus l by 2 to plus l by 2.
right,
So you have g m small d integral minus l by 2 to plus l by 2 dx by x square plus d square to the power 3 by 2.
right,
And this integral can be done by doing a change of variable. So the integral will be doable if you just take the variable x is equal to, see, the point is that there is a radical in the denominator, right?
yeah,
There is a 3 by 2 power and all. So
yeah,
I want to do something, some substitution so that I can remove the roots and all here.
yeah,
So the one way to do it is to use a trigonometric substitution. X is equal to d tan theta. If you do that, x square plus d square will be equal to d square sec square theta, right?
right, yeah,
So x square plus d square to the power 3 by 2 will be equal to d cube sec cube theta, right?
right, yeah,
And on top dx will become dx is equal to derivative from here is d sec square theta d theta,
right, yeah,
right?
yeah,
So the integral will start looking like d sec square theta d theta divided by d cube sec cube theta.
right,
So you'll get a 1 by d square outside integral 1 by sec theta, which is cos theta d theta.
right,
Cos theta integral is sine theta and 1 by d square comes out. And now I cannot put limits in sine theta because my limits was in terms of x.
yeah,
So I'll say I know the substitution that I did. Tan theta was x by d, right?
yeah,
So sine theta would be basically x by root over x square plus d square.
right, yeah, yeah,
So I will say it is 1 by d square x by root over x square plus d square. That is after integrating and putting back the old values. And now you'll do L by 2 to minus L by 2.
okay,
So when you do this, you'll say that on top you'll get L by 2 minus minus L by 2. You'll get an L on top, right?
yeah,
And you will get basically finally GMD L on top by D square and root over L square by 4, L square by 4 plus D square.
right,
X L square by 4 plus D square, right?
right,
This D gets cancelled like this and you get basically the expression Gm by D L by root over L square by 4 plus D square.
right, yeah.
This is the field, and the field is in the vertically downward direction because
Right.
all the components only in that direction got added up.
Right. Yeah.
The point is, this integral will be obvious to you in this year when you learn integration. It's fine. This is a simple substitution method.
Okay.
So note down this method, what we have done to integrate.
Okay.
It's not very difficult. It will become obvious when you do maths part of integrations. These are common integrals.
Okay.
What else?
Nothing. I haven't solved all of it yet.
So finish the exercise now, and once you are done with the exercise, you need to start studying chapter 29.
Yeah.
Chapter 29, volume 2, which is field and potential.
Yeah.
You will see that it is roughly the same thing. So it should be pretty easy to understand and figure out what is happening there.
Right.
Okay,
Okay.
fine. Next class, we'll be starting that and finishing any doubts in gravitation.
Okay.
Okay, fine. That's all
Okay.
for now then.
Thank you, sir. Bye.